Good. Okay, so ladies and gentlemen, welcome to this week's Monsoon seminar, which is going to be given by Anta-Clarisse Sarr, and she works. Sorry. Yes, it's going to be given by Anta-Clarisse Sarr, and she's going to talk to us about her modelling of the Asian monsoon. So without further ado, I'll hand over to her and ask you if you could mute yourselves and put your questions into the chat as we go along, and I'll call on you at the end. Thank you.
So hi everyone, and thanks Peter for having me today for this monsoon seminar and for this short introduction. So today I will speak about the South Asian monsoon evolution, focusing on the Miocene time period and the relation between monsoon winds, rainfall, paleogeography, and also all the system impact the surface circulation in the Indian Ocean. Sorry, this is work I've done during my postdoc at CEREJ, that is now over, and in collaboration with many of my colleagues here in France. And the presentation is largely based on a paper I published in Nature Geoscience earlier this year. So let's start by a short introduction on Indian Ocean climate dynamics, I would say, as this will be the backbone of the presentation. So in this basin, we have a climatic phenomena that we all know very well, which is the South Asian monsoon. Here we focus on the boreal summer seasons. And during this season, the monsoon is associated with the biannual reversal of cross-equatorial wind over the Indian Ocean. And so during summer, the winds, especially in the western part of the basins, blows from southwest to northeast in the northern part of the equator, transporting moisture toward the continental Asia. So this is the black arrow on the left, which is called the Somali jets. During the summer, so this peculiar pattern of atmospheric circulation is also associated with strong precipitation in India, Nepal, Myanmar, and Bangladesh. So and also over India. So this is the blue area on these pictures. From an oceanographer point of view, the winds are responsible for clockwise circulation in the western part of the basin. So this is the white arrows. So this circulation brings the water from the southern hemisphere along the coastline of Africa via the Somali currents toward the western Arabian Sea, and then all around the southern tip of India. The circulation triggers upwelling along shore coastline. So this is the pink areas, major ones being the Somali one, the Oman upwelling, and also the Indian upwelling. Then during winter, the wind reverses. The Somali jets then blow from northeast to southwest, but I will not show that on the presentation because I will focus on these summer seasons. The summer upwelling is responsible for increasing high biological activity along the coastline of the Arabian Sea. So this is the plot bottom right. And you can see here the regions with the strong biological productivity in orange, and they are also associated with strong seasonal, so with the bloom of productivity during summer. Because the upwelling happens at present day during summer monsoon, and in response to these peculiar atmospheric patterns, the strong productivity is often used to infer monsoonal activity over the region in the past. At tectonic timescales, meaning over millions of years of Earth's evolution, the coincidence between winds pattern, upwelling, and rainfall have been widely used to tell story about monsoon based on oceanographic proxies. And researchers did track the onset of strong productivity in the region, especially along shore Oman coastlines, in order to infer the onset of monsoon. The historical record is the one from De Kroon 1991. So this is the top right plot, where it shows the variations of percentage in Globigerina beloides. Here is the curve. And in this paper, the author shows that show an increase of this of the proportion of these foraminifera around like 10 to 8 million years ago that they interpret as the settlement or the strengthening of the upwelling system during the late Miocene. Here, same site, so the 722-730 Oman coastlines, but more recent study by Gupta 2015. So here again, you have the percentage of Globigerina beloides, on the bottom of the plot. And also the three top rows are the total organic content of the sediments. And here the author also depicts the appearance and increase of the proportion of beloides as soon as 12.9 million years ago. And this increase is associated also with increase in TOC, both likely translated, as I just said before, an increase in biological activity. And the author attribute this increase in biological productivity to what they call the onset of the modern-like summer monsoon. So biogeochemistry proxies have also been used on other sites to infer changes in monsoon dynamics during the mid-Miocene period of time. Here is a record from the Maldives archipelago, for example, a paper from Bessler et al. 2016. I don't remember the expedition name, sorry. Based on manganese-calcium ratio that is here interpreted as the strength of the oxygenation in the oxygen minimum zone that is also associated to upwelling activity tied to summer monsoon. And what the author shows in this paper is a strong decrease in this ratio at around 13 million years ago that they attribute to the settlement of what they call modern monsoon, meaning the settlement of the atmospheric circulation that is similar to present day. Same indicator have been also used alongshore Oman margin. This paper from Bialik 2020, but I will not show here there. All those records, so biogeochemistry records, in addition to records based on current indicators, are interpreted at the modern-like monsoon starting somewhere during the Miocene, like around 30 million years ago. And by modern monsoon, most of the authors from all those oceanographic publications specify that they refer to monsoon with modern atmospheric circulation pattern at least. That's boring, this. Sorry. All those records, in addition to record based on current, those paleographic records do look in contradiction somehow with terrestrial records that this time record a rather monsoonal rainfall. And those records suggest that monsoon-like precipitation, both in terms of trench and seasonality, occurred already during the Eocene, for example, based on Paleogeography analysis by Licht et al. 2014 in Myanmar, or by our colleagues from paleobotany. This is a paper, for example, from Bhatia 2021. And so there is kind of an apparent discrepancy if you consider that at present day winds and rainfall are specific of the summer monsoon season. So this discrepancy is kind of on the timing of monsoon evolution over time. And this is kind of a long-term debate in the field of paleoclimate and also science in general, as the timing of monsoon evolution, and especially the time of monsoon's onset, is a crucial things in understanding the solid earth evolution and the interaction between mountain belts in Asia and climate system. And basically everyone wants to have the oldest monsoon. So this is the main reason why I did start looking at this question and wonder what happened first to the upwelling system, because this is the main environment where a paleoceanographer derived the data for this monsoon evolution, but also what happened to general monsoon dynamics over this crucial time period that the Miocene seems to be. And I asked the questions whether we can find a way somehow to reconcile these two visions of the monsoon evolution over time. So for that, I use a paleoclimate, sorry, I will do that. I use paleoclimate model. So this type of model, for those who are not really familiar with, enable to reproduce the behavior of the climate system in response to impulse forcing, which is, for example, geography or CO2. And this includes, for example, winds, precipitation, oceanic circulation, but also sometimes biogeochemistry. In this work, I use a modeling framework that include a kind of typical ocean atmosphere model. This is the IPS LTM5A2 model, and also an offline biogeochemistry model for the ocean, which is the PISCAS model that I kind of force with ocean dynamics field, from the coupled simulations. And this enabled me to provide a systematic analysis of winds, rainfall, oceanic circulation, and also biogeochemistry, which is kind of very new for this deep time monsoon studies. And so it enabled me to compare kind of more qualitatively modeling and what we got from proxy data. I did perform a lot of simulation. We did perform a lot of simulation with this climate model under various paleogeography from Eocene onward toward the Miocene. And here in this presentation, I will show my work, which focus on the Miocene part. And I did perform different simulation, basically targeting change in paleogeography from interval around the 13 million year date. That seems to be very important in the paleoceanographic records. So this include early middle Miocene simulation. So this is the globe in the middle. This is a geography from Pobleté 2021, and also a late Miocene simulation. This is the right plot. And all the results I will show here are based on those simulations. So first and foremost, let's have an overview on the global trends we have on those simulations with the IPSL model. And this is also based on a paper we submit to a science review with Delphine Tardif as first author. So here, top row, you have paleogeography evolution from the Eocene to the Pliocene we used. And then bottom row, you have in color background the amount of precipitation during summer, and the red dots represent the monsoonal area in terms of seasonality. And what we see here is that those simulations always provide kind of a monsoonal climate over whole South Asia, with a lot of precipitation, and the area of monsoonal type of precipitation extending in size toward the Miocenes. So this kind of seems in agreement with the terrestrial proxy suggesting monsoonal precipitation already before the Miocene. Then if we look at winds, because this is what I've been interested in here, what we do see here is that for the late Miocene simulation, so this is the one that is circled with pink, we already have a pattern that resembles the present-day Somali jet, which is the right plot, with bending of the winds along the East African coastlines and strong winds blowing toward the northeast. Now, if we look back in time, this pattern is slightly different in the early Miocene simulation. This is the one in the middle, with more east-west wind in the kind of north equatorial region of the Western Indian Ocean, and winds that do not kind of go toward the northern domain of this sea. And then if we look in the Oligocene and Eocene simulation, the two on the left, we do not see this pattern anymore. This in response to changing the pressure of, pressure system in response to paleogeographic evolutions. So here we are kind of able to simulate a reorganization of the atmospheric circulation somewhere during the Miocene, as suggested from the interpretation of paleoceanographic proxies. That's why I will focus here on the Miocene evolution change, trying to understand also what happened in the simulation and how the upwelling evolved in response to those changes in atmospheric circulations, And also precipitation evolved, of course, during this time period, because precipitation is what is of most interest for many of my colleagues. So let's start first by biological activity, because this is what I targeted first in this study. So here the map shows the difference in export productions during summer between the late and the early Miocene simulations. And what you can see here, is that there is a lot more export production in the late Miocene compared to the early Miocene simulations. Looking at seasonal scale to better understand mechanisms behind this increase in productivity. So this plot on the right presents the variation of export productivity at 100-meter depth. From May to October, late Miocene is red curve, early Miocene is blue curve. And you see here that this increase in productivity in the late Miocene simulation is kind of sustained by the increase in productivity during late summer, while in the early Miocene simulation, the productivity remained kind of low during all this period of time. Actually, the productivity peak in the late Miocene simulation is driven by increasing nutrient content in the upper water column. This is the middle plot that is associated with increasing upwelling activity earlier in the summers. This is the bottom row, where you can clearly see the red curve having this upwelling peak that is almost the same velocity as the present day one simulations, while in the early Miocene simulation, the upwelling is very dampened and almost kind of non-existent in some early summer time period. Another way of looking at that, so here is what's happening in the water column. If we look at the two simulations, dashed line are the nutrient content in the first kind of, let's say, 200 meters, and the bold line are the productivity. And you can see here that the higher productivity in the late Miocene simulations in red is sustained by strong productivity in the first 40, 60 meter, where the productivity in these depths are hampered in the early Miocene simulation. And this is directly driven by the depletion of nutrient in the surface layer in the early Miocene simulation, so blue dashed curve, where you can see that there is no nutrient remaining in this area, in these simulations. So now looking at maps to try figuring out the link between upwelling and atmospheric circulations, because we are kind of able in the simulation to reproduce this increase of productivity associated with increased upwelling system during the late Miocene. So here is a map of the vertical velocity of the top layer of the ocean that can be assimilated to upwelling intensity. Right is the early Miocene simulation, left is the late Miocene simulations. And you can clearly see in the right plot that in the early Miocene simulation, there is almost no upwelling along the East African coastlines, especially in the Oman area, while you can see this strong upwelling along Somali and Oman in the late Miocene simulations. Apparition of the upwelling during the late Miocene simulation is associated in this simulation with the appearance of the strong Somali jet, with both the curvature and the strength similar to the present day. So this is the bottom left plot. And you can see that these strong winds are responsible for strong wind stress along the coastline that is kind of generating this upwelling. On the other side, on the early Miocene simulation, where we have almost no upwelling, what you can see is that the Somali jet, as I show at the beginning of presentation, is more zonal, east-west, and is not going above, let's say, like 7-8 degree north. So there is like kind of not a way to generate upwelling in these regions. In addition, what I show here also, because of this lack of strong surface circulation in the subsurface of Arabian Sea during the early Miocene, is super hot sea surface temperature, because the water, instead of coming from the south in the late Miocene simulation, this is the left plot of the temperature, they are coming from the eastern Tethys embayment, and they are super hot. So these results somehow suggest that paleogeographic changes is driving a transition in the monsoon dynamic, or at least in the monsoon circulations at that time period, mostly because paleogeography is the only difference between those two simulations. So cool, this kind of goes along with what people interpret from the data for once. And then I wanted to look at the potential drivers of simulated change, because most of the time everything related to change in the monsoon dynamic over the Cenozoic is attributed to the evolution of Tibetan Plateau and Himalayan regions. And what I do with those, what I did, with the simulation is that I kind of investigate the effect of different paleogeographic features that we know have evolved at that time period, two that are known to be able to drive a change in the monsoon phenomena because they have been studied mostly under present day geographic configuration. So in the late Miocene geography on the right, I did test the effect of closing the Tessian seaway, because we know that this seaway kind of been fully closed during the middle Miocene. And in the simulation, more specifically, I did investigate the effect of emerging lungs, in this region. I also investigate the effect of changing elevation in the Iran and Zagros regions. So here, the geological timing is more controversial, but some study evidence uplift activity rather recently during the middle to even the latest Miocene. And also because these features have been shown to have a strong impact of both circulation and precipitation in the monsoon region by Acosta and Huber 2020. On the early Miocene background simulation, I did look at the influence of Tibetan Plateau width and also Himalayas height, of course, as both theories are widely used to invoke triggering feature for the monsoon onset. And I also did look at East African topography states, mostly because we know it has an impact of the monsoon on the monsoon winds circulation from the study of Wei and Bodoni 2016, for example, and also because this one is widely uncertain given a few quantitative information exists on the paleo elevation. But we know that rift activity happened during the Miocene, and this should have somehow impacted the topography there. As I usually do not really know a paleo elevation in time, I do what we call a member simulation. So I use either the full elevation or very reduced elevation of those topographic features, because this enables me to maximizing the effect it has on the climatic system and to better understand the physics behind the change we simulate. So let's start by the early Miocene state. So I will always display the result as it is there on the left. So you have a map showing the wind velocity and wind pattern. Then I look at whether there is this Somali jet and OETs in the simulation, whether there is a normal upwelling, and then I also look at precipitation and seasonality. So I did start from this early Miocene simulation where I have east-west very weak Somali jet, what we can call proto-Somali jet, there is no upwelling, but there is a modern South Asian monsoon precipitation and seasonality. Then I kind of increase the height of the Himalaya, and what I see here is that there is kind of almost no change in the dynamics of the Somali jet. I still have no upwelling, but I increase the precipitation in the same region. And this is kind of what I would expect, because a lot of studies show that the precipitation amount in the South Asian monsoon region kind of scale with the height of the Himalayas. Then I did look at the East African topography, and what I show increasing the height of this topographic feature is that I am able to increase the strength of the Somali jet, but also more importantly that now this jet is a bit more bended and go further north. I still have no upwelling, but I have a decrease in precipitation in the South Asian monsoon region. This decrease is kind of controversial even in the modeling world, because different study trying the effect of these topographic features can show both increase and decrease in the same precipitation. Now let's look on late Miocene features. So on the left, I have a simulation where I have no Iran-Zagros plateau, and also I have kind of embayment in the eastern Tethys Seaway region. In this simulation, I have a very weak Somali jet, although it's already banded because I have the topography in East Africa. I have no Oman appalling, and I have a South Asian monsoon, a typical precipitation, the mountain seasonality. Then I close the Western Tethys Seaway, and I increase the amount of land we have in Arabian plates. In this simulation, I have an increase in the jet, and also what is not well shown here, the jet is steered northwards and reach the coast of Oman. And here I have an Oman upwelling, but almost no change in the precipitation in South Asian monsoon region. Then increasing the Iran-Zagros topography to its full elevations have kind of a cool results, because it showed that these topographic features enable to increase a lot the strength of the Somali jet. It also intensified the Oman upwelling and increased the SAM precipitation, which is kind of the results I would expect, because Paul Acosta in his 2020 paper also show the same thing, and the kind of mechanism behind that is that increasing the topography of Iran-Zagros kind of block the winds, the very dry wind coming from the north to enter the monsoon regions and kind of shelter the moisture there. Things I wanted to show before going to more discussion on upwelling, monsoon, and paleogeography during the Neogene is to go back to rainfall quickly, because I have shown so far that our model kind of do simulate change in atmospheric circulation in the monsoon region in response to Miocene evolution. But what you have alongside this change, kind of reorganization in the atmospheric pattern, is almost no change in the monsoonal rainfall. By no change, I mean that in all those early and late Miocene simulation, trying the effect of different topographic features, I have this very seasonal climate with strong precipitation during summer, although the amount of precipitation during summer may vary among the simulation. This suggests that this monsoonal rainfall is kind of a feature that we have indeed before the Miocene, as shown by terrestrial proxies. So what I would say kind of in summary is that those modeling results shows that Himalayan and Tibetan plateau region and configurations, although they are big and a superstar in the field of paleoclimate and geoscience in general, is probably not responsible for changing the monsoon dynamic that we show in the Miocene, especially if we look at winds evolutions. And also probably because the uplift that is important for the wind system occurred earlier, meaning that those topographic features are already high enough in the Miocenes, so the monsoon rainfalls are already there. But the study rather shows that the monsoonal rainfall also is tied to what happened in the Iran-Zagros region. I think that is kind of super important. On the other side, why it has been so largely overlooked in most of the paleo study, some of the western boundary topography that are very less well constrained can have a huge impact on the atmospheric circulation pattern in these regions. So this is the case for Iran-Zagros, this is the case of Iran-Zagros topography. And I also showed that the feature that is very important when looking at the early dynamics of the Oman upwelling is what happened in the West Tethys Seaway and West Tethys embayment. So this diverse topographic driver for both monsoon rainfall and monsoon we might explain why we do see a different timing between terrestrial rainfall records and paleoceanographic records that are mostly tied to oceanic circulations. And this also means that we clearly need to define what we mean by monsoon on geological timescales, whether we mean winds, whether we mean precipitation, or whether we mean both, and then we can start discuss when monsoon onset. And so this is one of my last slides, and maybe the one I like the most. I would say that to better understand what happened in these super cool Indian Ocean basins and what happened with Asian monsoon, we need to take into account much more what happened outside of the Himalayan, Tibetan Plateau regions. But for that, especially when we look at climate modeling results, we need better constraints on all those Western boundary topography, not to say about the maritime continent and ITF regions. And we also need paleobathymetry and paleoaltimetric estimation, because this matters for the way we understand the monsoon system. And this is my take-home message. So I would say that this modeling study kind of tend to show along paleoceanographic records that modern-like monsoons, meaning monsoon with both present-day atmospheric circulation and rainfall, is likely a neogene phenomena. But this does not prevent the fact that monsoonal precipitation occurred before that. I would also say that a pooling is not always a good tracer of monsoonal rainfall activity, especially on tectonic timescales, but it provides information on the pattern of surface ocean current circulation, and therefore on the pattern of atmospheric circulation. And I would finish saying that topography and physiography outside Himalayas and Tibetan Plateau regions really matters for monsoon dynamics. And this is a call for my paleo geographer colleague and geologic colleagues that we need more data on those features. And thank you very much for listening. And I would take all the questions you want.
Thank you very much. Good. Well, if people want to type their question in the chat, we can come to that in a minute. And so I was curious, I don't know if this is a fair question to ask you or not, but I was intrigued about this emergence of Arabia, which, I mean, I understand that Arabia is colliding with Eurasia and that the deep water would be cut off, but I guess I was surprised to see that your reconstruction showed the whole of Arabia like underwater in the early Miocene, and I wondered what was the evidence for that, especially as I would have expected uplift where we get uplift in East Africa related to the Afar hotspot, that I would think that would have uplifted southern Arabia as well. So are you confident about that?
I would say like this, I mean, the rift in East Africa and the fact that indeed these Afar things should have uplifted the Arabian plate as well is true. And so we have the mountain belt in this southern part of Arabia. What I mean by emerging Arabian plate is kind of saying that alongside closure of the seaway, we kind of switch from shallow sea toward land, and this make a huge difference.
Oh.
And this is what what is in the paleogeography. And I think I would say I'm kind of pretty confident that before the closure of the seaway, there was land, there was sea, sorry. And what I'm not confident about is the amount of land, of course, there. And I don't think there is a lot of data from this time period in this region, unfortunately.
Yeah. The importance for the upwelling in Oman is quite interesting, isn't it? That's quite dramatic. I wondered also if you could say something about what your thoughts are about the Indonesian through flow, because I often thought, well, if you're allowing, if before the closure of the gateway, hot water was coming from the Western Pacific into the Indian Ocean, that should have an impact on the monsoon. So do you think that that's going to be an important influence, or you were talking a lot more about the influences on the western side of the monsoon region? Do you think that Indonesian through flow will be important?
Like for what I've studied here, like the Arabian Sea part of the monsoon, I would say Indonesian through flow do not matter most. Maybe it would matter for the amount of precipitation we have over whole India, because all that depends of the moisture content of the atmosphere, that is also dependent of the sea surface temperature, sorry. But I have issue with this Indonesian truth flow, mostly because when you change that in the model, nothing happens most of the time.
Okay.
And also, I guess that the timing is a bit different from this 13 million year date, because closure of the deep water is probably before that. And then what matters in terms of climate then probably locates much more during the Pliocene than during this mid-Miocene monsoon thing.
Cool. Thank you. So now we have a question from Paul Wilson. Paul, do you want to just unmute yourself and ask your question?
Thanks, Peter. Really excellent talk, Anta. I think I've said this before. I think it's a very compelling paper, and the experiment that you laid out is very elegantly done, very systematic and comprehensive. And I like the fact that the whole study starts with that you kind of identify this very fundamental kind of mismatch in proxies. I mean, I was going to ask the same question that Peter asked about Arabia, because my colleagues who work on afar always emphasize the uncertainty over the timing of the full docking of Arabia and its emergence, and particularly the timing of the transition from shallow sea to land. So, but maybe we can talk a bit more about that in detail when you come to visit. But so my question for now is, what happens in winter? Okay, so for very obvious reasons, your talk focuses on the summer.
Yep.
I'm just curious, because of our interest in dust records, we're also very interested in what happens during winter. Is it as simple as, well, when the summer monsoon gets stronger, the winter one, kind of the winter winds also get stronger? And is there kind of any directionality change associated with these changes in tectonic boundary conditions?
I would say that it's for sure not as simple as increasing summer monsoon, increasing winter monsoon, probably also because they likely do not respond to the same geographic features, given that they have like different wind directions. And so I do not remember from these simulations, because it's been a while, I haven't looked at that and decided not to focus on winter monsoon for biogeochemistry issue most of the time. But I should look at that before coming and see you, definitely. But I guess like the Iran-Zagros, like the change in Iran-Zagros topography that I have in my simulation would probably kind of impact the wind coming from the north, I would say. So maybe, I would have different in kind of circulation pattern during winter, also in those Miocene simulations.
It would be great to take advantage of your trip to kind of have a look at those sorts of issues in a bit more detail. I'd be really interested to do that. But let me. There may be others who wish to ask questions while they have the opportunity. So let me stay quiet for a second.
If anybody else wants to ask a question, now is the time. If you want to say something else, Paul, you're very welcome. I think we don't have any obvious takers.
Okay. Yeah. I mean, I think the other thing could you just, I'm interested in the past, I suppose. I guess one of the motivations of your study is that it draws on the very classic work done in your group in East Africa on
Yeah.
a kind of younger part of the record. Could you sort of just maybe talk a little bit about, you know, the different, your study kind of focuses on the early to late Miocene transition. That's what we talked about today, pretty much. What about is there, is that what is what happens later significant to regional climate in a really important way? Is post-Miocene change important?
You mean post-Miocene change in the paleogeography?
Yeah, in East Africa, you know, you said that I wrote down that you said that there was a sort of threshold level of 1,200 meters. So maybe just expand on how on the sensitivity of the system to that threshold, and you know, maybe also talk about how well understood the timing of the attainment of that threshold level.
Yeah, exactly. So the threshold is what I have in the model,
Mm-hmm.
meaning that I am able to modify the surface circulation, like not really the surface circulation, but the low level of the atmosphere circulation. As soon as we have this crossing the thresholds, like about 1,200 meters. This is because those low-level jets, which is the case of the Somali jet, is below this elevation. So you kind of, in order to kind of cross the thresholds to the into the in the circulation, you have to kind of cross this peculiar elevation, meaning that if you are below 1,200 meters, the Somali jet pattern is kind of very east-west. And as soon as I go above this elevation, I'm able to interact with the wind now, and I kind of block the wind from the west. So they have to go a bit northwards before going like into the Indian basin.
Mm-hmm.
No, this is true only if the kind of Western Tethys Seaway region, Arabian Sea Peninsula has a configuration when you have a lot of shallow water or deeper water in this region. As soon as you have the present-day configuration of the Arabian Sea, it doesn't matter whether there is Africa topography at very high elevation or intermediate elevation. I know about these thresholds in the model, mostly because I did try different elevation, like 700, 1,200 and more. And then I look at the pattern and I notice this happened there. No, the issue is that we have almost no paleoaltimetry data in East Africa. I mean, I think there is only one at 17 million years in Kenya, I would say. But this is almost the only thing we have. All the other estimate of elevation there is based on modeling work based on like mantle dynamics things and so. So this is a real problem, not knowing the real timing of it. And I think it's really important to know whether this high elevation in East Africa is reached like before or after the closure of the Decian Seaway in order to better get what happened in the system.
Right. Okay. Well, that's really interesting. Thanks very much.
Welcome.
So, if there's no other questions, we will bring this seminar to a close, but I want to announce, so next week we have a lecture by Torsten Haberzettel, and he's going to talk to us about something quite different, about monsoon on the roof of the world, talking about ICDP drilling in Lake Namcho in Tibet. So please come back for that. It's at the earlier time, the European morning time, the Eastern Hemisphere time. But please come back. And if you can't come back, look at it on YouTube when I send you the message. So anyway, thank you very much. Please put your hands together either using your hands and or the online feature in Zoom to thank Anta-Clarisse for her excellent presentation. Thank you. And stay safe, and I'll see you all before too long. Thank you. Thank you. Thank you, Anta.